Okay, where did we stop? So, okay, we talked about motion in 2D. So it's called kinematics 2D, and we are focusing on projectile motion. Okay, projectile motion meaning along the forward motion, the forward direction, it's moving at a constant velocity. There is no force, but at the same time, along the vertical, up and down, it's in free fall. So you always have two situations. Either it's free fall, like you drop something, or it could be also that you get mad, or you just uh, launch something like up and down, right? So we have two sets of equations totally independent from each other's except for the time. Okay, and I show you a methodology how to do it, right? So we did that. Here you have to understand that they will reach the ground at the same time, okay? Because the two motions are independent from each other. Remember that the velocity along the x, it's very annoying here, hello, the velocity along the x stays the same. The velocity along the y is going to increase at a constant rate, which is -10. So every second, the velocity along y is going to increase by 10. We're going to call that the y component of the velocity. That's going to be the x component of the velocity. Okay, so we're going to talk about vectors. So just to, I just have like, what do I have? I have a simulation. Hello. So we already have seen that. So this one has no launch velocity. So the projectile, which is a cannonball, will just drop. This one, we're going to give it a large launch velocity. Okay. But along the y, it doesn't have any velocity. Okay. So the initial velocity along the y equals 0. It's just along the x. So we launch. And you see, they are both falling at the same rate. So they will reach the ground at the same rate because the forward motion doesn't give a blank to the down motion. They ignore each other. Okay, it's not that intuitive, and that was found by Galileo, right? He said that any motion in 2D and 3D, okay, can be divided into components along the x, along the y, and along the z, and they are independent from each other. Now, I could, if I want, I can make one just drop, and this one with an angle like this. So in that case, of course, this one will reach the ground first because this one now has an initial velocity along the y. So it's not just dropping along the y, it's going up and then it's going down. So along the y, they do not have the same equations because in that case, you have an initial velocity along the y. If you follow the formalism to divide like the two motions into two sets of equations, then it's not that hard. Okay? Okay, so let's do an easy one. Let's do this one. So I have no idea how realistic is this. You have a antelope and there was a cliff here and she jumped, but lucky for her happens to be a mattress here. So it doesn't hurt itself. What's going to be delta x? So delta x is called the range. So if in your textbook it's called the range, okay, uppercase R. Okay, so it will be the x displacement. Okay, the displacement along the x-axis. That 30 meters is the height, so it's a scalar. However, in the equation, you want to write down negative 30 meters. It's a vertical displacement. And you want to make an x and a y. So, of course, it's an easy example, but just to lay out the methodology. Right? So once you have the right methodology, then it's not that hard. So again, you want to do it. Yeah, so try to do it now.
If this were a word problem, would it say to look for the range?
So yes, you could say find the range, sorry, or find x displacement, or no, it will say how far in front of the cliff it will land. You can make it more tricky by changing the words, right? So it could say how far from the cliff on the ground will it land.
I just wanted to know because that's
Okay.
something important to recognize.
Yes, yes, it is, because then they can trick you with the wording, right? So first you want to do the x and y. So once you have your always have a x, y. Okay, of course, that's going to be plus. That's going to be plus. And what else? So, okay, it's already done for you. What kind of situation? It doesn't have like free fall, right? It doesn't have an initial velocity along the y, because it doesn't, get mad, like push downward. It's not suicidal. So it's going to be a situation where it's in free fall here. And that will be just forward, which is cruising. It's just cruising. Okay. So 1, 2, 3, it's good. I'm going to change that to 10. So we have two sets of equations. Here we always have delta x equals v initial velocity times t, and I'm missing the time. So I need to go sneak here, right, and ask for the time. Agree? And then you have your equation of kinematics for free fall. It's doing two things at the same time. It's cruising forward, but it's in free fall with an initial velocity equals 0. So they ignore each other. So here I'm going to find the time first, right? So I'm going to find delta y equals initial velocity. So just to remind you, that will be free fall. Just happened that the initial velocity equals 0. It doesn't, go down. So it's going to be minus, it's going down, but there is no component of the velocity down. So it's minus 5 t squared. So that will be negative 30 equals minus 5 t squared. So t equals square root of 30, which is, no, 5. Okay, is that clear? Do you all agree? Don't stare. What you are staring at? Just do it. It's just nothing new. What is 5? It's a kinematic equation. Okay, remember a kinematic equation is 0, 0 t minus 0.5 acceleration t squared. Acceleration is always minus 10. Free fall, so you always get minus 5. Okay, so you get 2.4 seconds, right? Make sure you open your textbook. Yes. What? Yeah, but no. The displacement doesn't have to be the same. Only the time will be the same, right? You can someone can jump from a very high cliff here, and do something like this. So your delta x here will be smaller than your delta y. So they don't have to be the same. What has to be the same is the time. Do you agree? Make sure not to erase your USB key for physics like over the weekend. Save. Yeah, you have to save it, right? 2.4. So delta x will be 60 times 2.4, which is, well, thank you, 147. And I rather you asking for an extension than asking ChatGPT for the answers of your assignment. Because if you don't try the assignment, you are not building the foundation for the next classes, right? It doesn't stop with physics. My class is easy to pass, but that's not enough. You need to build up, because then you will have, like, if you want to be an engineer, they will have tech interviews, and they're not that easy to pass. So anyway, so those two, that projectile motion has two independent components. So if something is rolling off the table like this with a horizontal velocity, it's going to describe a projectile motion, which is half of a parabola. Okay, along the x, the velocity stays the same, it's cruising. Along the y, the velocity is going to increase at a rate of -10. Now, if you drop something here at that same level, then the velocity is going to increase exactly with the same rate, and they will reach the ground at the same time. So last time I show you videos, so I'm not going to go over that again. Are you with me? Okay. Um, oh, okay. So using speed photography, like high-speed photography, you can see that it's true, right? They are falling at the same time down. Okay, same thing here. Even though they do not have the same horizontal velocity, they will still fall at the same rate and reach the ground at the same time. The only difference, obviously, is that this one will reach further than that one. Okay, I refer you to the video I showed you last time. Okay, so this is a classic in Physics 1. And so just to understand that two motions will happen at the same time along different direction, but everything is falling at the same rate if they start the motion at the same time. So anyway, it's the story of the monkey. So I don't know if you heard that story. So he's aiming at the coconut because, of course, now we have to be careful not to hurt anyone feeling. So instead of, before it used to be killing the monkey, but you don't want to kill monkey anymore. So it will be aiming at the coconut, right? So as soon as he trigger the gun, the rifle, which is a BB gun, okay? So as soon as he hits the trigger, he gets scared. The monkey gets scared and let go the coconut. Do you understand? So the projectile here is leaving the rifle at the same time as the monkey is letting go with the coconut. So they are both falling. Do you agree? Okay, we neglect air resistance. So the projectile here is falling and the coconut is falling. If you want to hit the coconut, do you aim above the coconut, at the coconut, or below the coconut? It's very good. The answer is at, because they are both falling at the same rate. So along the y-axis, they are covering the same distance during the same time. So I'm going to show you that. So it's a classic, the monkey and the hunter, the monkey, but now it's the monkey and the banana, or the monkey and the coconut. So now it's the monkey and the banana. Okay. So I'm gonna aim above, just a little bit above here. No, missed, right? So I'm gonna aim below. Okay, missed. Now I'm gonna aim at the monkey. And you see, because along the y-axis, they are both falling at the same rate. Okay, so the the projectile here is doing two things, right? It's gonna move one unit and fall one unit. The banana is falling one unit, and then next it's gonna move one unit along this direction, but now it's falling 3 units. The banana is also falling 3 units, and then next is moving one but falling 5. The banana is falling 5. And then another step, it's falling 7. The banana is also falling 7. So they will be at the same place at the same time. Even if you increase the speed, so here I'm going to increase the speed. I'm aiming at it. Isn't that cool? Right? So if I ask you conceptual question, do you have to aim above, at, below? The answer is at, as long as, yes, you're right. So they're gonna do that experiment here. I wish I could do that experiment. I don't have the material. So they're gonna put a monkey here, and it's being held by a magnet. Okay, and here you're gonna aim with a golf ball, but as soon as you trigger, it's an electromagnet, so the magnet will let go. Okay, electricity is cut, and it will drop. So as soon as you trigger, the monkey is gonna fall. So you're gonna see a slow motion. Oh, so it's a very nice demo to do. Okay. Okay, let's take an example here. Again, tennis. So tennis, you want to make sure that you start your projectile motion from here, and you want to make sure that the velocity here will be large enough just to make it here, to clear the net. Okay, so you want to find that horizontal velocity. You know the height of the net, which is 1 meters, and you know that displacement, that distance is 10 meters, and you want to find that velocity here to make sure the tennis ball makes it here. Okay, so do it, not that hard. So that if you love physics, it comes from a very, very good book, which is called Conceptual Physics by Paul Hewitt. He's very good. He draw the situations himself. He's very famous, Paul Hewitt, right? You can read about his story. His story is very interesting because his professors in high school told him, you're not you should not go to college, right? You're good at drawing, go draw things. Go be an artist. And then he didn't listen, went to college and became a professor. So sometimes you should not trust your professors too much. Paul Hewitt, you can Google Google his stories. On YouTube, he tells his story. So x-axis, okay, no, y-axis. So no one gets mad here. Okay, so it's just falling. Simple free fall situation. X-axis, it's moving at a constant velocity. Any problem, it will be always -10 because it's projectile motion. Initial velocity here, I'm going to put a y because it says it's going to be along the y. That's going to be 0. What else do you know? Displacement, very good. Delta y -1. Okay, we have to be careful with the x, y. So that's going to be negative. I'm going to put 1 because that's pointing down. Agree? And then let's take that 10 meters. 10 meters is along the x. So it has to be here, delta x equals -10. And then initial velocity, I decay.
Wouldn't it go in all the direction?
Yes, you're right. 10. Thank you. And then you always have that equation here. Okay. I want to find delta x equals, no, delta x I know, right? So do it. Don't look. So 10 equals V0x. I do not know. And the time I do not know. So when you don't have the time, you're going to sneak. And you ask, here, find me the time. Okay, so look at your kinematics equation. You don't have many, you have 3. You have the displacement, then you have the acceleration, and then you have the velocity square. Look at your equations. You want one, the only one with the time, or the 2 with the time, is the first one and the second one. Do it. Take your first equations of kinematics, replace a by -10, replace x by y. It's not hard. It's not that hard, right? You have your kinematic equation here, and this one is just cruising. So here you will always have that equation here. Always. Projectile motion, always. So delta y equals, very good, -5t squared. Initial velocity is 0 because no one is getting mad at the tennis ball. It's not being pushed downwards. So delta y is -1 equals -5t squared. So t equals, huh? Yes. Yes. Good. Agree? So once you find the t, you go back. You go through the tunnel here, and you say, here you go. So 10 equals the x component of the velocity times 0.45. So the initial velocity here is 10 divided by 0.45 along the x is, very good. So that component here is 22 meter per second, and then you're gonna have a projectile motion with a horizontal initial velocity. Now, if you want to see if it makes sense, remember that 2.2 miles per hour is 1 meter per second. So if you have 22 meter per second in question mark, so 22 meter per second times 2.2, you cross multiply, okay, 48, so about 50 miles per hour. That will be for someone who play tennis, right? Not like, yes, you have, yes. So if you are a pro, it should be like 90 about.
There's an X and a Y. What's the other?
But here we only have X and Y because we are doing it in a plane.
Yes, what about the back?
The what?
Back.
The magnitude of what? So the distance, the displacement, the magnitude of the displacement is called the distance because distance is a scalar. The magnitude of the displacement is called the height. Okay, so height and distance are scalars that will be in the real life. And the physics life, you have displacement, or math life, you have displacement, x displacement, y displacement, because they are vectors and sign matters. But in the real life, you just have height and distance, which are scalars. Right? Questions? We good? And I cannot emphasize more that you need to do the problems in your textbook, right? So Newton was a genius, if you watch the video, okay? He came up with gravity. He understood orbits, the first one. And that comes from his Principia. And of course, at the time, it was not in color, but that's what he drew. Right? So obviously, he was a genius. So he figured this out. If you have let's say you have a mountain here, very high mountain, and you have a projectile that you launch horizontally, just horizontally. Okay, so there is no initial velocity along the y. So it's in free fall. So it's falling at a rate of -10, right? So we figure this out. If you launch here, it's going to come back. It's a parabola. And if you increase the launch velocity along the horizontal, so along the ground, you're going to hit farther. Okay? If you increase the velocity even more, it's going to hit even farther and then even farther. But if you get it just right, it will never reach the earth because the earth is curving away at the same rate that the projectile is falling. Okay, so he figured this out, that if you have the right initial horizontal velocity, it will go into orbit. Okay, you can launch even further, I mean, uh, with a higher velocity, and then you can make an ellipse. And then even more velocity, then it can break free from the earth, right? It's called the escape velocity. So if you have enough velocity, you just make a parabola, like you break the ellipse and it will make a parabola and you escape. So obviously he was a genius. I don't know if I have like Newton. So I have so many stuff. So many stuff. It's very hard to find. So Principia, okay. You see, you increase the horizontal velocity, and at some point you can go into orbit because the Earth is falling, so curving away from the projectile. Isn't he a genius, right? He invented calculus as well. He also, like, so conic section, if you take a math class, I'm sure you have to learn about conic section. You have the circle, the ellipse, and the parabola and hyperbola. And Newton was able to show that anything moving in space, okay, if there is gravity around, so if you have a star, a planet, or whatever, the motion has to be along a conics. So it could be a circle, an ellipse, a parabola, and a hyperbola. So they are called conics. That's from the Greek, right? So if you cut this way, you have a circle. This is a cone, ellipse, hyperbola, parabola. So if you have enough velocity, okay, you can just break free and escape to space. You can break free from the Earth, and you will follow a parabola. If you have a speed larger than the escape speed, you will follow a hyperbola and go to the moon or wherever it's going. See, falling and then still falling, but now the Earth is curving away. Enough velocity, so now it's an ellipse. You go into orbit around the moon. So all you need to do that is Newton's physics, right? So anyway, so what do you think here? So you have your projectile, okay, and you know that the Earth is curving away 5 meters. So it means if you have a run of 8,000 meters, the Earth is falling 5 meters. So what do you think the velocity should be for a projectile to go into orbit? Okay, let's find out. So you want to make sure that if you launch, if you are launching a projectile, okay, so it has a horizontal velocity here. So it's going to do two things at the same time. It's moving at a constant velocity along the forward motion, but it's also falling. Okay. So x axis, y axis. So you want the projectile to fall at the same rate as the Earth. So the delta y, so acceleration equals -10, the delta y equals -5, initial velocity equals 0. What's going to be the time it takes to fall 5 meters for a projectile? So projectile in free fall, how long does it take for the projectile to fall 5 meters? It's easy. Don't stare. 1 second or delta y equals -5t squared. So, oh, it should not say that. So -5, because they give you the answer, equals -5t squared. So t equals 1 second. Yes? Now, delta x equals 800 meters. The time is 1 second. What's going to be the velocity? Yes. It just means that if you launch your projectile at a speed of 8,000 meters per second, the projectile is going to fall by 5 meters every second. So it's going to fall at the same rate as the Earth is falling. So if you want to have a projectile in orbit around the Earth, the minimum speed should be 8 kilometers per second. So if you watch the first video that I like the video that I asked you to watch, remember Newton said that the moon is also falling toward the earth, but never reaches the earth. But it's falling, right? So if you have the moon, no, you have the earth and you have the moon. The moon wants to keep going in a straight line at a constant speed. No, you can't. You're gonna fall, right? I want to keep going straight line at a constant speed. No, you can't. You're gonna fall. So it's constantly falling toward the Earth, except that the Earth is curving away. So it will never reach the Earth. So Newton unified gravity on Earth and in the heaven. Um, I will leave that for the assignment. I don't know if I should do this. Any question? So definitively on the test, right? So this slide is in my Dropbox. Okay, are you buckle up? Let's buckle up. I'm gonna go back to vectors. We already talked about vectors. In 1D, it's easy. It's right, left, up or down, positive or negative. But now we're going to do it in 2D, which means you will need trig. Okay? So we're going to divide a vector into its components. Now we'll explain that. So a vector has a tail and a head. It has a magnitude, how much, a unit, and a direction, which way. Okay, so it has a head and a tail. So the tail, you always want to attach the tail to the x-axis origin, so it doesn't fly away. So easy, which quantity is a scalar, is not a vector, which one? So a force is a scalar or a vector? A vector, okay? And speed, scalar, very good. Acceleration, very good. Displacement, it's a vector, right? Distance is a scalar. Velocity is a very good. We already said that. I don't know why I have to. Okay, so let's take some examples where vectors are useful. So this is the wind, and this is called a vector field. So every point in space, you're gonna define, you're gonna have a direction, which way, a magnitude, how strong is the wind. Direction, which way it's blowing, how strong is the wind. Usually, ideally, you want to make the length of the arrow proportional to the speed of the wind, but then it gets very messy. So instead, they are using colors here. Okay, so but that's called a vector field because anywhere in space you can associate a vector. So vector field. So very useful in fluid what it's called, fluid mechanics, for example. So if you have a bathtub, you see the water is gonna spin and faster and faster and faster and faster, right? So you can show that rotation here using vectors, how fast the fluid is rotating. Now if you take advanced calculus, which if you are in engineering, you will have to, I don't know if it's called calculus 3 or 4, but you will learn about a way to compute how much rotation do you get inside a vector field. This is called curl, okay, or rotation of a vector field. How much rotation? So you can use mathematics, to define how much rotation is there. Okay, so that will be the curl of the velocity. So is it rotating in that case? Do you see something rotating? Is it spinning? This is a gravitational field. Do you see? No. What is it doing? Very good, converging. Okay. So in that case, there is no rotation. So the rotation, the curl of the field is zero. So we can define it's called the divergence, the operator. So anyway, it's just converging. This is like we call that a source. Okay, it's converging toward the source, and that will be a gravitational field. Okay, gravitational field. See, as you move away, gravitational field is getting weaker, but that will be a vector field as well. If you take physics 2, you will learn that a positive charge, for example, will generate that electric field. And what is it doing in that case? Is it converging or diverging? Diverging. So you can define an operator in math called the divergent. So it's you can say how much the diverging do I get? And you are right, they are repelling each other, and what you see is that they have been lying to you. You think that positive and positive, they just act instantaneously on each other, right? You push me, I push you, but actually it's really the field interacting with each other. So it's a vector field. It's very important for mechanical engineering, I guess. And here you have an example in 3D. Okay, so I'm not going to play.
Lie a little and artificially shorten ones that are too long. Maybe using color to give some vague sense of length. Now, in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields. What was unsaid is that you can often understand a vector field which represents one physical phenomenon, an idea which regularly goes.
So here you have in 3D. So this is something that you can do easily with a Python, like Python library. They let you, it's easy to draw like those vectors and show how they change with time. So anyway, this is called a vector field. Are you with me on that? So you need your trig. So I'm not going to teach trig because I told you to go over that. So let me take an example here. You have New York and New York City here and Detroit. So you can make your vector here A, B. Okay, it has a direction, and the direction is 10 degrees north of west. Okay, so I can define my vector as 600 miles, 10 degrees northwest. Do you agree? But that will be for a bird. You're not a bird, so you have to take the highway. And let's say you have a highway going this way, and then you have a highway going that way. That will be called the horizontal displacement. It's going to tell you how far did you go westward. Okay, so this is called the x component or the westward component. It's going to tell you how far did you go in that direction, but at the same time you are going north, so that will be called the y component. how far did you go up or north in that case? Okay, so vectors come into components and each component has a special meaning. To find the components, we have to use trigonometry. So otherwise there is a trick, but let's say you know your trick. So for example, here you have that notation AB, okay, will be 600 miles at 10 degrees northwest in the real world, right? So that will be X and that will be Y. That's going to be your 10 degrees. But in physics, we like to go from the positive x-axis, okay, and we like to go counterclockwise. So I'm going to put the vector here along the positive x-axis, right? I'm going to go counterclockwise, counterclockwise, counterclockwise. I stop here. What's going to be that angle here? Just 10 degrees above the horizontal. It's going to be what? 170. Very good. Okay. So you always go counterclockwise. That will be 90, 270, 180, sorry, 270, 360. I'm so happy I don't have a frozen shoulder anymore. Can do that. You know, when you get older, you get frozen shoulder. It's not fun. So anyway, standard notation will be AB equals 700 miles at 170 degrees. So if you write it this way, you know that you have to go from the positive x-axis and you go counterclockwise. So this is called the standard notation. If you use that standard notation, meaning the angle that it makes from the positive x-axis, then the x component will be always the cosine and the y component will be always the sine. Or you can use trig. But if you use that notation, then the x component will be always cosine, the y component will be always the sine. You with me? Only if you go counterclockwise. So if I go back to my slide here, okay, so this is called the polar graph. You go from 0, 90, 180, 270, 360, right? If you use that angle here from the positive x-axis, then x component will be always a cosine, y component will be always a sine. You can use trig also. You don't have to use this trig. So you see here, just a reminder, that will be 0. That's 45 degrees pi over 4 in radians. Pi over 2 is 90 in radians. 3 pi over 4, pi, blah, 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 3 pi over 2, nya, 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 and 2 pi. Okay, radian is just a unit. It's like degrees. 360 degrees is 2 pi. Are you with me? Okay, so that's one notation. The other notation, you have your vector. The tail is attached at the origin. Okay, so what's the meaning of the component? I can find that point here. That point that the head is showing, okay, that will be my x component. That's going to be my y component. So can you find the x component and the y component? So you can say 600 cosine 160, or you can use trig. So I want to find this point here. Okay, I want to find this point here. So this point will be your run. that point here, okay, will be the x component. That will be your x component. So from the tail to the head, you run, boom, 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 and then you rise, you go to the head. From the tail to the head, that will be your y component. That's the x component, which is westward in that case. And that will be north. How far did you get north? How far did you get west? Okay, so the x component will be 600. You can say cosine 10. This is cosine 10. Do you agree? You used your right angle triangle. So you can say 600 cosine 10 and you have to put a negative, or you just say 600 cosine 170. So what you get? Thank you, Mice. Do you agree? So it means you walk, or you maybe not walking, drive 591 miles westward. Okay, I'm sure I'm going to get the question. Why can you do cosine 10? Yes, you will get the same thing, but then you will have to do a -1. Okay, you will get the same thing. So that will be 591, but you have to remember to do -1. Yes, you have two ways to do it. You can use your trig skill, or you can do just 600 miles, 600 cosine 170. Do you all agree? Yes.
So 591 by itself will be wrong. So 591.
Yes, because good question. If you do 591 by itself, it means this direction.
591.
So yes, so in the real world, that's what we want. 591 west. If they talk about north and south, west, and yes, so that will be correct. Because you need a direction. Yes. So 600 is the vector. There is no, the direction in that case is 600 at 170. There is no plus or no minus, because you see here, you have to go into components. So you always have to break a vector into its components. Either you use this notation or you're going to use that notation. But there is a -600 if it's in 1D. So if you have 600 here, then that here will be -600. But if it makes an angle, you have to break into components. So let me finish for the y component, the northward, right? And then you will see it makes sense. So what's the y component? Huh? What? 104 miles. Or 100 miles north. So here I'm going to put -591, and here I'm going to put 104. Okay, so that will be that point here. Now, if you are in the real world, you will say 591 west and 104 north, because it's doing two things at the same time. Agree? So you cannot say -600 if you are in 2D. Okay, so here it says study vector unit 1, textbook 1.5, 1.6. So make sure you open your textbook. So two notation, the standard notation, but the angle has to go from positive x-axis going counterclockwise. And the other notation here, it's in the polar graph. And you want that point here. Okay, so vector comes into components. So I can show you, for example, here. Or I don't know what is it calling. It's a sled. Thank you. It's a sled. He has to put some clothes on, right? So that's the pull, right? But that pull is doing two things at the same time. It's going to move the sled forward with that force here. So that will be the X component of the force. That component here is busy trying to accelerate the sled and is busy trying to fight against the friction. Of course, you have friction. That makes the things interesting, is the friction. Now you have another component. And what is the other component doing? Very good. It's lifting. The Y component here is lifting. They are ignoring each other. They don't care about each other, right? So that X component is pulling forward. This one is lifting, and lifting is always easier. Why do you think it's better? Like when you pull, you're gonna decrease friction, right? So if it's something very heavy and you pull, nothing will happen. But it's better than pushing, because if you push like this, you put into the ground, so you're gonna increase the friction. So that's why we need components, right? With that component, we will be able to find the acceleration, if it's strong enough, given the friction. Okay? And the Y component is busy doing something else. The Y component will have to fight what? What is pulling down? Gravity, right? So along the y-axis, you're going to have the y component will cancel out the gravity, the weight. Now, if it's moving at a constant velocity, that means the x component is just balancing out the friction. He's very strong. He will be able to overcome friction and accelerate. So you will have a net force. Isn't that interesting? Another example here, when the Usain Bolt, right? He's not human. Uh, he was able, and that's all physics, by the way, he was able to deliver a huge amount of energy in a very, very small time. So that means power. So that means he was able to deliver a huge momentum, impulse, right? Huge impulse. And I don't know if you know, there is biomechanics is super interesting. So a lot of physics, right? So you have the muscle here, and the muscle you have fiber 1 and fiber 2 and fiber 2. And fiber 2 you have the what is called the muscle twitching, the fast muscle twitching, right? So it's explosive. So you are able to deliver a huge force during a small amount of time. So physics says, and that's from Newton, force times time equals a change in momentum. So if you make this one very small, you can make this one huge. So it means during a small amount of time, he was able to deliver huge force, right? Very, very powerful. So anyway, when they are running here, so the force here, you're pushing, so it's going to push you back. So there is a force here. And you want to make it at the right angle, because it has two components here. So that component here, along the x, it's going to provide what? During that very small time, what's going to happen to your speed? Increase acceleration. So the component of that force will provide the acceleration. So you're going to see x component. But at the same time, you don't want to fall. So you still need a small y component, but just small enough, not too big, because otherwise you're going to lose time going up and down. Just right to be able to lift and start a motion. And that isn't that interesting? So this is called explosive, right? It's a explosive because you are delivering that force during a small amount of time, and that will be fiber 2 muscles twitching, muscle twitching, explosive. It's like an explosion. In addition to that, to increase the physics, here you have a tendon and then you have the muscles. You have the muscle here and then you have the tendon. And the tendon is like a spring. So they are training their tendon, they are training that spring. So when you compress the spring, you can store what kind of energy? Huh? Potential energy, elastic potential energy, right? So it's like a kangaroo. So you compress the spring and boom, you deliver a huge amount of energy during a very small amount of time. And the muscle behave not the same way. You have a spring here, and then you have the muscle, and the muscle doesn't move that much. It doesn't contract like this and that, right? It stays about the same, and everything happens with the tendon. So you have to be special. Maybe it's genetic, okay? So they have to train their tendon to be very, very elastic, to be able to store all that energy, boom, deliver in a very small amount of time. So the people have studied Usain Bolt. He's like a study case. Ah, interesting. So is it in the tendon or is it the muscles? Oh, so fiber too. Ah, that's interesting. So, so what's the country? It's, oh, Jamaica. Oh, okay, okay, okay. That's interesting. What's your name? Michael. Yes, interesting. So sometimes it's the genetic, right? So don't feel bad if you cannot do it. Blame the genetics. So a lot of physics here. So I learned that fiber 1 and fiber 2. So fiber 1 is endurance and fiber 2 is those muscle twitching, right? And then fiber 2, you have fiber 2A, fiber 2B, and fiber 2X. No, they added one. The fiber 2X, it means it's the people who are doing weightlifting. The because you have to train your muscles, so you kind of change the fibers inside. Okay, let's go back. But this is called biomechanics, right? It's a lot of physics, very interesting class. So anyway, so you have a vector. It has a magnitude and it has a direction. So if you need, you can play with this here. Okay, so that will be your vector. Attach the tail to the origin. That will be the x component. So it's like you rise, you run. Your rise will be the y component. So A will have two components here. So it's not that hard. You can increase the angle here. Okay. So counterclockwise, you open. So 162. So if you do 120 is the magnitude times cosine 162, it's going to be a negative. And then if you do 120 sine 162, it's going to be positive. Agree? But you already know that because I told you to open your textbook. So if you have a vector, okay, let's say you have a vector here, the first thing you want is to make sure it doesn't fly away. So you want to attach the tail to the origin. That will be your first step. So you have your vector here, and then you can find the components. These are the components, or these are the components, right? So that will be the x component, and that will be the y component. So 10 to the left, 9 up. So that point here at the head will be minus 10, 9. Agree? Okay. the angle, it depends, like, so, okay, so in that angle here will be 138. So if you do 13.5 cosine 138, you will get the x component. If you do 13.5 sine 138, you will have the y component. Okay? And I have the link in Canvas if you need to. Okay. Vectors textbook 1.6. Again, x component, y component, and you should be able to switch from one notation to the other one. Okay, so if you have the x component and the y component, then you can find the magnitude using Pythagorean theorem and using the tangent here, opposite over adjacent. But sometimes it can be tricky, so you really have to draw your vector. Okay, so let's do something quick. Can you find the x component of B and the y component of B? Quick. You have two ways. The standard notation ways, or you can do the... Are you doing it? Because I'm lost in my notes. I don't know. Okay, let's do that. So you good at trig, you don't need the polar graph. You're not good at trig, then you take your polar graph and you draw your vector B. Agree? Okay, so you have two ways to do it. Okay, so B has a magnitude of 15 meters at, so that will be east of north. But if I put that 60 here, that will be my standard notation. Do you agree? And then to find the x component, you just do 15 cosine 60 or 15 sine 30. Okay, it's called complementary angle, 60 and 30. So cosine 60 is the same thing as sine 30, right? Sine 30, same thing as a cosine 60, because 30 plus 60 is 90. So if you do 15 sine 30 or 15 cosine 60, what do you get? Very good, 7.5, that will be the x component, and then 13 will be the y component, and the units, I'm going to place it here. Agree? Okay, so if you have C, for example, it has a unit of 12 meter at what? 180 plus 25. Which is 205. Okay, so C has a x component of, so you can say 12 cosine 205 or 12 cosine 25, negative 10, negative 11, negative 10 or negative 11? So negative 11, and then you do 12 sine 205 and you have negative 5. Okay, be careful with the negative. Okay, so it's doing two things at the same time. It's moving to the left, so you run. From the tail, you want to get to the head, and you go down. So this is 11, and this is 5. I don't put a minus because you already have the arrows. Okay, so that point here is minus 11 minus 5. Okay. Note that 20 cosine 25 is the same thing as cosine 205. They are supplementary. Not supplementary, but you take away 180. And it has to be in absolute value because one is negative and the other one is positive. But if you take the absolute value, you get the same thing, except here you have to be careful to put a minus. Agree? Yes.
Why did 13 for B?
What is what?
For B, it's 7.5 and 13. Why did 13?
This one because it's 15 sine 60.
160?
It's 60. 60. This is 60 here. 60 degrees. Okay, so if you take the polar graph, this is 30, so that's going to be 60. And if you want to use the trick, you want to make sure that your vector is inside your polar graph. If it helps, you can print out the polar graph. What about this one? Does it have a x component? Does it have a y component? Which is what?
Negative 8.
Minus 8, right? Negative 8, right? Because sine 270 is 0. Okay, so let's do just to practice. Let's do this one. Number 1. Quick. Ah, I need to finish all that. Help each other, talk to each other. So the first thing you do is always x and y. And they talk about west and north. So this is north and this is west. 36 west. Boom. 36 west. And then it says 22 north. Boom. 22. Okay, so this is the x component, y component. And the vector has a tail that wants to be attached here, otherwise it flies away. Yes, Pythagorean theorem. So that will be my vector. But you always want to draw the vector to know exactly what you are talking about when you are talking about the direction. So be careful here. We're going to see that it can be tricky because now we are doing the opposite. Instead of going from the standard notation to the polar notation, we go from the polar to the standard. So V, x component 22 west, which is minus, no. So you can say 36 west, 22 north, or in the mathematical world, you would say minus 36 plus 22. Okay, what is the magnitude? So magnitude, I'm going to put absolute value, and you need to use Pythagorean theorem. Which is 22? 42, thank you. 42 meter per second. So that length here, that's called the hypotenuse, is 42. Do you agree? Now to find the standard notation, we have to be very careful with the angle. Because Of course, now we want to find that angle here. That's why you have to draw. So we use tangent opposite over adjacent. So let's find that angle here. Okay, tangent. It's called SOHCAHTOA. Tangent is opposite over adjacent. Adjacent, hypotenuse, sine, cosine. Huh? 32? 36?
No.
31. So 30. Let's make it easier. 30 degrees. But if I'm gonna write here V equals 42 at 30 degrees, then people are gonna be confused. They're gonna think that I'm gonna talk about this angle here, right? That could be 30. So we don't want people to be confused. So instead we are using the standard notation. So if you use the standard notation, you go from the positive x-axis and you go boom, 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 boom. So that's going to be the angle. This angle here is what? 1. So this is 180. This is 30. 150. Do you agree? Because you have to go counterclockwise to make sure that people, when they're going to read your report or whatever you are writing about, they understand that you are talking about this one. Now, if you are in the real world, then it's fine. You're going to say at 30 degrees northwest. So those are acceptable. Physics world and the real world. Agree? Okay, so you always go counterclockwise. So this is acceptable. It depends on the multiple choices. Sometimes they will say northwest, like the MCAT. They love northwest, and to know that you know the compass here. Or you can use that notation here. Okay. So just on top of your head, you are jumping, or the boy is jumping 25 degrees above the horizontal. So how do we find the horizontal component? 20 cosine 25. Very good. Okay. You make it jump this way, so it's easier. Okay. So in that case, it's an airplane. And you see that it's doing two things at the same time. It's moving at launch when it's taking off. It's taking off. It's moving forward, but at the same time it's moving upward. Okay, so if you have an airplane, that angle seems dangerous to me. Not happening. Like a lightweight airplane will be 20 degrees. Usually it's like 10 degrees, like otherwise people are gonna throw up, right? So it has two components, X and Y. And so it's moving forward, so it's going over delta X, and it's moving upward. So imagine you have the sun here, so you're gonna have a shadow. The shadow of the airplane is going to move forward at a constant velocity, say, and at the beginning. So you can find how long it's going to take for a shadow just to be above your head. So in that case, you're going to use the X component. because it's doing two things at the same time, moving forward and moving upward. We say that it's moving at a constant speed, although it doesn't. But so find the x component of the velocity and find the y component of the velocity. It's easy, right? So for the x component, I'm going to use 650. And then what? Cosine. So if it's in the first quadrant, I don't have to worry, right? 650 cosine 20. And the y component will be 650 sine 20. Okay? And conveniently, I can divide the motion into two components. The delta x, so, that distance here will be the x component times the time, and the height, so that delta y here will be the y component times time. So you can decompose any motion into its components. So if you take an algebra 2 class, this is called parametric equations. Okay, you have two equations and then you can combine them in one. Okay? So let's do this one. That's called, I don't know what it's called. This is called that Miami, they do that. They sailing car. But can you see that this one is lifted above the ground? Do you see that? Okay, let's see why. It's because of the components again. Flipping or flying? Just flying? No, flipping, right?
No. Like
Really?
it starts taking off, yeah.
Really? I didn't know that. Like the sailing car? The
It's hard because the way that they are designed. I don't remember it right. I was speaking over soon.
Interesting. So it's misengineering or it's supposed to fly?
It's misengineering. It gets too much air under it and basically ends up taking off for a good second. It's not good for the drag.
Oh, it has to be with the lift. The lift from underneath, right? So this is 60 degrees. That will be the force applied on the sail. So again, you have this picture here. This is what's happening, right? The wind is pushing on the sail. So you see that two things are happening at the same time. It's moving forward, okay? So that's good. You have an x component of the force, but at the same time, it's pushing sideways. So that's why here the one of the wheel does not touch the ground. Okay? Because it's doing two things at the same time. It's pushing this way, lifting, okay, y component, and it's pushing forward. So you move this way, but at the same time, you will be only on two wheels. Are you with me? Okay, so what's the standard notation? Quickly. The magnitude is 400 Newton at, so what you're right, that's 300, yes? 300. What's your name? Mark. 300, yes. Standard notation, that will be 300. Once you have the notation here, so the x component is easy, it will be 400 cosine 300, and the y component 400 sine 300. Newton. Agree? So that point here will be, you're going to have two components, x component and y component. So make sure if you have not done it that you open your textbook